Look at the outer edges of this spinning spiral galaxy. Based on the visible matter, gravity is too weak to hold this structure together. The edges should be flying apart into the vacuum. This chart plots the velocity of galactic material based on its distance from the center. Newtonian physics dictates a steep drop-off in speed the further out you go. But the observed reality is this flat, horizontal line. The outer edges are spinning just as fast as the core. Standard cosmology embeds this visible galaxy inside a massive, diffuse spherical halo. This is dark matter, theoretical exotic particles that do not interact with light. Physicists have spent decades and billions of dollars building massive underground detectors to catch these weakly interacting massive particles, or WIMPs. Yet, despite all this effort, those giant detectors remain completely empty. We have extreme confidence in the mathematical models requiring extra mass, but absolute lack of physical evidence for the particles themselves. Astrophysics currently relies on a ghost particle to hold the universe together. It is time to look at the missing mass problem through a different lens. The structural cosmology hypothesis offers a purely astrophysical alternative. It focuses on the ordinary baryonic matter we can actually observe in galaxies like Andromeda. This framework identifies the missing mass as dead matter, the cold, inert remnants of the universe's first stars and primordial black holes. A physical theory is useless without testable predictions made before the data is collected. During an interview on the Demystify Sci podcast, the author of this framework laid down a specific time-stamped marker. Microlensing less than a day, primordial black holes, population 3 remnants. Dark matter is going to go away soon. True science demands risking being completely wrong to prove a mechanism right. This public prediction subjects the framework to a measurable audit. But how could ordinary dead matter mimic the exact distribution of a theoretical dark matter halo? This is the structural cosmology modified halo profile. It takes the standard profile and applies new modifiers. The critical variable is Tau, representing local proper time dictated by gravitational time dilation. In higher gravity regions, time moves slower. Over 13.8 billion years, this time dilation gradient acts as a dynamic trap. Cold, drifting particle clusters of dead matter are caught and accumulate densely in these deep gravitational wells, where time takes slower. Applying this time-modified distribution flattens the rotation curves of galaxies like the Milky Way and Andromeda, with a superior statistical fit, without requiring a single new particle. The missing mass anomaly is an illusion created by treating time dilation as a passive kinematic effect, rather than an active, accumulative force that shapes cosmic structure over billions of years. This model relies on one highly debated assumption. Time is an emergent, local property, rather than a fixed, universal backdrop. In 2026, the Barontini experiment provided a physical test of this exact temporal mechanic, using ultracold atoms. This schematic maps their Bose-Einstein condensate experiment. It demonstrates time emerges from localized quantum interactions and entropy, rather than a master cosmic clock. This data directly validates the tau parameter in the halo equation. The foundational assumption of structural cosmology now stands as an empirically demonstrated physical phenomenon. With the mechanics validated in the lab, the next step is locating the physical dead matter out in the galactic halo. We map invisible mass using gravitational microlensing. As shown in this diagram, when a massive object passes in front of a background star, its gravity bends the light, creating a temporary spike in brightness. The duration of that spike is strictly proportional to the square root of the passing object's mass. Recall the specific prediction: a population of substellar primordial black holes creating microlensing events lasting less than 1 day. Shortly after that prediction, the Key et al. Publication announced the detection of a candidate object named Phoebe. Phoebe generated a microlensing event that lasted exactly 60 minutes. The data points to a lunar mass object drifting in the Milky Way halo. Statistically, the Key et al. Data shows this object is 100,000 times more likely to be a halo dark matter object than a stray star. These tiny, ancient black holes provide the gravitational scaffolding for the cosmic web, acting as the initial seeds for early galaxy formation. We can see the results of that seeding process in this James Webb Space Telescope deep field image. Webb recently discovered early universe supermassive black holes that formed far too quickly to be explained by stellar collapse. The exact class of dead matter required by this theory has now been observationally located exactly where and acting exactly how the framework demanded. Finding a single lunar mass candidate is a strong indicator, but confirming a universal model requires population-level statistics. The upcoming decade of advanced microlensing surveys will serve as the ultimate unforgiving trial for this hypothesis. The first strict threshold relies on the Nancy Grace Roman Space Telescope, which will conduct the Galactic Bulge Time Domain Survey. To survive, the model requires Roman to detect in excess of 30 to 300 short-duration Earth mass microlensing events by 2033. The second threshold relies on the Vera C. Rubin Observatory, pictured here mapping the southern sky. The framework requires the Rubin Observatory to detect 50 to 600 long-duration solar mass events. Their spatial distribution must map to a spherical halo, rather than a flat galactic disk. Structural cosmology has willingly painted a target on its own back. It has provided the exact mathematical thresholds that these upcoming observatories will test. Here is the falsification matrix. If Roman detects fewer than 10 Earth mass events, it falls within the background noise of rogue planets, and this hypothesis is dead. But if the data crosses the threshold for confirmation, this log-normal curve permanently replaces the WIMP particle model. Validation of this model identifies the missing mass as ordinary, ancient matter. The missing gravitational glue is no longer a mysterious new particle. The dark matter we have spent half a century searching for is ancient matter, rendered invisible by the cold void and trapped by local time. The solution to this mystery is waiting in the dark, ready to be counted.
Does it feel like we're just making it through?